Yo, dude! What are those? Oh my god, they're gorgeous! They're beautiful, oh my god, I love them!
Yo, look at this other thing! It moves with these tiny little things!
What is that? It's warm, it is bright, it is... Oh, I want to touch it. But wait, what is me? What is all of this? Where am I? So, these are examples of a few infamous questions. We find them simple because we already know the answer to them, and it seems obvious. But it isn't. Reality is extremely complex as it is. But, as it is, how is it then? Is it how we perceive it, how we interpret it, or maybe is reality a thing that exists whether or not we are aware of it? We don't know. Well, either way, it is clear that we as human beings are in constant desperation of trying to catch a glimpse of reality, to find the truth, to understand reality. We try to measure every little thing in reality to predict its behavior. With this intention, we try to base things around some constants and rules that we can prove and apply always in any circumstance. And so it began the quest to finding an answer to the question, why are things the way they are? And we started with the conception of tiny little balls merged together, and that makes our world. Those are the particles that make our world. Then we added the conception of charge to those particles. Then we discovered that they have a nucleus and something surrounding it, and there are interactions of electricity and energy inside. And then we discovered that there are three fundamental particles there, the protons, electrons, and neutrons. And then we discovered spin. Yeah, spin. And then we understood the fact that we know nothing about fundamental particles. That's the thing. They're uncertain. Uncertain in a sort of predictable way at some place at some time. But they can also be two things in space at the same time, juxtaposed, and we know nothing about them, but we do know something. That is the point that we are at. The epitome of physics, the highest point in the conception of things, the Standard Model. Even though we don't know if the laws of physics are going to break sometime in the future, for now this thing that describes things and the relationship between things and all the things and the functioning of things is the best thing we have for comprehending how things work. It's all about things, you know? Things.
The Standard Model of particle physics is basically the explanation of three of the four fundamental forces and the classification of the known elementary particles. In a few words, the Standard Model is a recipe for creating the universe with 12 particles and controlled by three forces. It is based in the conception of symmetry and is regulated by it. The start of this theory is matter, or more precisely, elementary particles. We all know and acknowledge the existence of atoms and its subparticles, protons, neutrons, and electrons. But not everyone knows that these subparticles can also be divided. Using particle accelerators, hundreds of subparticles were discovered, crashing them against each other and observing the aftermath. Now, they are known as fundamental particles and are divided into fermions and bosons. Fermions are described as building blocks of atoms. They are something that is somewhere at the exact time. Therefore, two fermions cannot be placed in the same space, but they can collide with each other, and they are also subdivided into quarks and leptons. Bosons, on the other hand, are the responsible for carrying energy, and in the contrary to fermions, they do not care about space-time, and two of them can be placed in the same space at the same time. There are different types of bosons, and each one corresponds to one of the three fundamental forces: the electromagnetic, the weak, and the strong forces. Now, we've already mentioned the fundamental forces a couple of times, but what precisely are these forces? Well, the universe presents fundamental forces and governs everything that we've done and will ever do. These four forces are gravity, the weak force, electromagnetism, and the strong force. But for studying the Standard Model, We only consider the electromagnetic, the weak, and the strong forces, because everything breaks when you include gravity. Do not mess with it. The electromagnetic force includes the electric and the magnetic force, and it explains how stationary charged particles interact. The weak force is responsible for the charge of a subatomic particle into another type, while the strong nuclear force is responsible for binding fundamental particles together. So, in very, very few words, this is the standard model of particle physics.
So, fundamental particles. Even though there are more than 100 years of progress in the completion of the standard model that explains all fundamental particles and the functioning, it has been completed since a few years back. Just in 2012 we discovered the Higgs boson, and I know that that's what we're talking about today, but first, for explaining the Higgs boson, we need to understand some things first, and these things are the other fundamental particles, the quarks, leptons, and bosons.
Hi everybody, my name is Nicole and I'm going to explain you what those quarks are. When you hear the word quark, I guess you like imagine quarks and a small dog saying quack 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 a lot, but no. For understanding this, we've got to go a long time ago in history. Well, not that old, but when the scientists find out that the smallest particles in all the universe were the electrons, the protons, and the neutrons. Scientists were like, oh yeah, I discovered the smallest particle in the universe. And then there was this man that I guess had nothing to do or nothing to spend his time on, because he passed a lot of days, months, researching and doing experiments and all that kind of scientific stuff, and find out that the smallest particle in the universe was not nor the electron, nor the proton, nor the neutron. And there were these little things called quarks, which all the atoms were conformed of. So, a quark is used to give to a proton or a neutron its charge. First, we need to understand that there are 6 different types of quarks: the up, the charm, and the top. And these quarks generally will have the 2/3 charge. And then there exists the down, the strange, and the bottom, which will have the -1/3 charge. And we also have the anti-quarks, not the evil ones, but that have the opposite charge. Instead of 2/3, we've got -2/3. Instead of -1/3, we've got +1/3. Okay, so quarks can work alone. You can find a quark there flying in space like, hey, may I join to your group? No. Okay, so we have groups of 3 and we have groups of 2. The groups of 2 are conformed by any quark and its antiquark, as easy as that. And the groups of 3, well, this group has something to do with math, and right now I will explain you that part. So let's see. Here we have a neutron or a proton, whether you want, and the circle that now you have seen is the amount of quarks that a proton or a neutron can have. Only 3 or only 2, but we have already explained that. So for a proton, we need to make that all the quarks summed or added get the number of 1. How do we get that 3 different parts summed get 1? Well, easy. We do fractions. Which fractions have I already told you? The ones of 2/3 and -1/3. Okay, for doing a proton, we're going to use 2 up quarks and a down quark. So we have up, up, and down. Or the charges that are 2/3, 2/3, and minus 1/3. Something like this. Sorry for my numbers, I know they're horrible, but what can I do? Well, now, if we want a neutron, then we're going to add another different combination of quarks. We're going to add one up quark and two down quarks. And when we sum all these numbers, we're going to get 0. So, it's easy as maths. We gave the charge to the neutron or the proton by doing maths. It's not as difficult as that. Finally, we've got two very weird but like crazy properties of these quarks. The first one is the asymptotic liberty, which okay, let me explain it with my fists. Okay, so we have two quarks, or three, whatever. Two quarks. As long as they are getting closer together, the force that makes them get closer becomes less, and less. And by the time they are both touching themselves, the force is neutral. There is no force, they are just joined together. They are practically free, but they are joined. The smaller the space is between these two quarks, is the smaller the force we're going to have. And there's the other property called the confinement. And this one is like the opposite. As long as we stretch the space between these two, we're going to get a stronger force. But there will be some point where all this force will rip, will pop, and instead of having one large pair of quarks, we're going to get two small pairs of quarks, and that's how they work. So, in conclusion, quarks are used for giving the charges to neutrons and protons. They can be positives, which are the normal quarks, and the antiquarks that are negatives from the positive ones with the same charges, and they can be in groups of 3 or 2. And I guess that's everything. Thank you.
Okay, so these are some basic concepts about quarks. They consist the strong force and make all matter that we know, protons and neutrons. But the fact that there are only 3 inside a proton or a neutron is kind of misconception, because there can be all millions of quarks getting inside and outside the neutron in such a beautiful mess that we cannot comprehend. But we know that inside these protons and neutrons, these quarks that get inside and outside cancel each other out. So the only remaining 3 are these quarks, upper than quarks, that consist of the matter of the neutron and proton. So these things seems quite a lot, but they only consist 1% of the total mass in things around us. What are the other things?
Okay, so by now we've explored every fundamental particle which interacts with the strong force. But that's only half the story. Up and down quarks make up most neutrons and protons. But neutrons and protons don't make up atoms in themselves. There's a pretty important ingredient missing. Electrons! Of course, and electrons do not interact with the strong force at all. That's why they don't get pushed into the nucleus. Instead, they orbit it and are solely responsible for chemistry. Chemical reactions are the exchange of electrons. Well, you might be wondering, what if neutrons and protons get exchanged? Well, that's actually nuclear fusion, and electrons make it hard. The thing is, electrons are tiny, like super duper tiny, almost the lightest thing in the universe that actually has mass. This means their orbits around nuclei are extremely large in relation to their size. And yeah, that does mean matter is mostly empty space. It also means under normal conditions, the chances of two nuclei crashing into each other are extremely low. But not everywhere is normal conditions. In the heart of the sun, things aren't gas, they're plasma. Hydrogen atoms are moving erratically at incredible speeds and are much more likely to crash into each other hard, fusing into helium atoms. This powers the sun with nuclear fusion. It'd be kind of cool to have nuclear fusion back here on Earth, don't you think? You know, powering the future and stuff, but we would have to have the little suns on the Earth's surface, which I think we can all agree is a pretty terrible idea, right? Or is it? Yes, it is. It's a terrible idea. But fortunately, there's another way to do it at non-crazy temperatures, and it's all thanks to the electron's bigger brother, muons. The second family of leptons. That's right, I'm finally name-dropping the mostly negatively charged, not interacting with the strong force class of fundamental particles. Leptons, that's what they're called, alright? Electrons are just the main one and the only stable ones. But muons are essentially the same, just a lot heavier. And you know what that means, right? It means their orbits around nuclei are way closer to the nuclei themselves, making the crash between nuclei much more likely to happen. Legitimate nuclear fusion at not crazy temperatures exists and has existed for almost 70 years at this point. But it's not very useful for us in terms of generating energy because muons aren't stable. Okay, we can have electrons everywhere, but muons we kind of have to create ourselves if we want to have a supply of them. And creating them takes more than twice the energy we can really gain out of nuclear fusion induced by them. So unless we make it way cheaper, let's say energy-wise, way more efficient to create muons, muon-facilitated nuclear fusion isn't going to be the source of electricity for the present or the future. Then there's also tau, the third family of leptons. They're a little bit heavier than muons, a little harder to find, and there's not much practical use for them right now. They're basically just helping us prove the standard model further. Yeah, they're fine, okay? I don't want it to seem like I have a preference, but I'm sorry you ended in a low note, alright?
Okay, so we already covered the particles that consist the weak force, that is, quarks and leptons. But we're talking about now about the strong force, and that manifests in the particles that we call bosons. Bosons are pure energy, and they can come in different flavors as quarks. So there are four. The first one is photons. Photons are massless. They are pure energy. They're beautiful and they're warm like a summer breeze, and they're just as easy as it because they can travel the universe at light speed without bumping into things. Then we have gluons. They have a self-explanatory name. They are glue. They bind together quarks, and they work in like a Y-shaped thing in protons and neutrons, with one up quark and two down quarks binded by these gluons. Then we have the W and Z bosons that, like the tau particles, they exist for explaining a little bit more the standard model. The W boson regulates the absorption and emission of electrons and positrons. It kinda relates to the transformation of protons into neutrons with the transformation of its charge. Then Z bosons are neutral. They are zero charge. That's why they are the symbol of a Z. And well, they are in charge of transformation of spin, momentum, and energy of the fundamental particles. And both of these bosons can decay into quarks very easily. They are very highly unstable. Well, those are bosons. Okay, so now the Higgs boson. But before we begin to talk about it, we have to understand something very, very important. And that is that particles, as we know them, are not a sphere. No, they are not a sphere. They are very more complex than that. They are a manifestation of alteration in some place at some time. There are energy that disturbs a field. But what is a field? What do we talk about when we talk about love? I mean fields. We talk about like a swimming pool with water in it, and when we add something to this pool, it gets disturbed, right? You add energy, some energy that disturbs the water. You submerge it, and it causes alterations in this field, so that you know that this thing is present there, and you can sense it, right? Because the field manifests it. Now, there are different types of fields, but this time we're going to talk only about the Higgs field. Therefore, the boson of Higgs. So, I talked about fields, didn't I? Well, these things cover the whole universe and are the place where particles manifest themselves. Right? Right. Now, the Higgs field is sort of the place that gives particles its mass. Therefore, it's a place where mass expresses itself. In this field, particles can travel with more or less ease depending on its mass. So that's why a photon can travel through it just as easy at light speed, and an electron can't. An electron is slowed down by this field that restrains him from moving. But how do particles interact with the Higgs field? Well, this is due to a characteristic fundamental of the particles that is called hypercharge. This characteristic is related to spin, and it affects the particles when they are moving through the Higgs field. They are sort of changing its spin, and they are slowed down by this. The more mass they have, it is hard to explain because we need to talk about parity and other things, but sort of this is the thing that happens. Let's say this rise is a Higgs field, and this needle is like a photon, a particle with no mass or very few mass. So it starts to move towards the field, and it barely very manifests its presence because it has no mass. But let's say this is an electron or a quark, and we put it here, and of course it makes a disturbance. Let's imagine this every rise is like bombarding the electron or the quark with hypercharge, and it changes its spin and lowers it, and it can't move as fast as the proton because of the high amount of mass. And that was the Higgs boson in the Higgs field following the Higgs mechanism. A lot of Higgs going on here, am I right?
What? Reality is beautiful. So there are tiny things. Why? There are big things. It only gets harder and harder to get it. Now, okay, then things just makes no sense. Things that are things because they exist. Not at all. This thing manifests in things, and things manifest in it, and everything is energy. How did I end up? It's okay in this rabbit hole. You can rest.
Yeah, so in summary, physics has still a lot of troubles with parity, dark energy, dark matter, and the expanding of the universe and some other things. It has a lot of problems. But the standard model seems to be the chosen one by the gods. The prophecy says that he will come save us all from the calamities of not understanding everything. And, well, the chosen one is in diapers. And we can only give him love and give him understanding to raise him and let him marry himself to gravity. And finally we can catch a glimpse of a theory of everything. That's what we need. Answers. And yeah, that's pretty much it.